And the other thing is that we talked about in the mechanism that's on the board, we talked about actually we form a diol before we do this step, right? And then we form the final carboxylic acid. So the mechanism, oh, here's some pictures of chromium trioxide, acid, which is often sulfuric acid or hydrochloric acid. Acetone makes chromic acid, or sodium dichromate with sulfuric acid makes chromic acid. So basically, when you see Cr and anything else, it's always this, okay? Okay. So this is what they show in the mechanism. All right, they show this. You have the chromic acid with the alcohol, fast and reversible chromate ester. The steps that I put in here with the protonating of the chromic acid and the attack of the nucleophile and then the water leaving, right? They left all those steps out. There's the formation of the chromate ester. And then water or some base in the mixture will attack the hydrogen and do an elimination reaction. So it's an E2 style elimination. And that's how you'll get the carbonyl functional group back. Okay? Does that make sense? Like, questions? If you have questions, feel free to ask. Okay, so one compound that's worth mentioning is this compound called pyridinium chlorochromate. They make it from chromate. They're showing how it's made. And pyridinium ion, or chromium trioxide and pyridinium ion. Pyridinium is the cation for this. And let me just draw the structure for you really quickly so you can see what it looks like. And then we'll discuss why it's different. I'm trying to find a good place to put it. I'll draw it up here. So pyridinium, I'll just draw that out. And then the chlorochromate actually is this. It's exactly the same as chromic acid, except, right, in two key things. No hydrogen here. No oxygen here. Okay? So, if you go back in the chromic acid oxidation, all right, let me draw it. I'm going to draw it again here just so you can see it. Oh, and I'm going to cheat. I'm going to write PY plus. Not really cheating, I'm abbreviating. So this replaces this. All right, so this hydrogen has been replaced by a protonated pyridine. Okay? And this oxygen hydrogen, this hydroxyl group, has been replaced by a chloride. So when you do this reaction, what do you think leaves on the PCC? What's the best leaving group? Yeah, the chlorine, right? The chloride. So when the oxygen attacks, right? If I were to draw an arrow like all the way over to here, the thing that leaves is this. When that happens in the chromic acid oxidation, what leaves? Water, right? Okay, now, the thing that the water happens with the water, though, is when you're on a primary alcohol, that attacks the aldehyde and forms another alcohol, right? And then you get aldehyde to carboxylic acid conversion. But there's no source of water when you use PCC. So if you use PCC and like methylene chloride solvent without the addition of any water, and you take a primary alcohol, okay, what's going to happen? Well, it'll oxidize it to the aldehyde, and then it stops. Okay? When you just use chromic acid, you can't stop it. It always goes to the carboxylic acid. You can't isolate the aldehyde in between because the aldehyde is so reactive. So what PCC does for us is gives us a way to take an alcohol, a primary alcohol, and produce an aldehyde out of it instead of a carboxylic acid. Okay? So, in other words, I have two things that this makes available for me. By the way, secondary alcohols always go to ketones. Okay? But a primary alcohol if I use PCC, and this is because I don't have any water present and no source of water in the reaction, okay, will form an aldehyde. Try that again. I don't know why I'm doing that like that. There we go. Or I could go Jones reagent. Remember, Jones reagent is chromic acid, but I just want you to learn, like, you might see it this way on an exam, you might see it as the other. It'll completely convert it over to carboxylic acid. I don't know why I drew the carboxylic acid that way. It just felt fun. Right. Of course, one of the questions that came up yesterday was, well, why do you want to do that? And the answer was, depends on what you're trying to do, right? Turns out aldehydes are really nicely reactive, and you can do Grignard reactions with aldehydes. So you can add R groups to an aldehyde and form an alcohol. Sorry, I got too many bonds in there. I don't know what to write there. Let's put R, like an R group from a Grignard. Turns out Grignard reagents won't react very well with carboxylic acids because it's an acid. It's a proton source, right? But it turns out, too, that you can take carboxylic acids and you can make esters out of them. And another really, there's a bunch of functional groups that you can convert that into. One of the really handy ones, I'll draw it this way so it's a little easier to see, is you can make an acyl halide, and those are very reactive, okay? And so you can convert that into all kinds of different functional groups. And you can react it with Grignard reagents. There's a lot of things you can do with acyl halides. What do you think the reagent is from going from here to there? No, not HCl. Yeah, so what do you forget all the time? Because you learned it, like, alcohols are bad functional groups for substitution, but you can use this other reagent and you get thionyl chloride. Yeah, SOCl2. Same, you already know how to do this reaction because you know how to substitute an oxygen on an alcohol with a chlorine. You can use like PCl3, I think it's PCl3 that you can use with this as well. That's the, is that another one you forget?
No, that's the one that I...
That's the one you remember? Yeah, because it's PCl3. Yeah, it's not thionyl what? Yeah. Yeah. Okay, so, yeah, principal use for PCC is to take primary alcohols to aldehydes. When we used it in lab this semester, I just used it because it's a little bit easier to use, but we could have just used chromic acid too. So I'm going to convert this into two questions, actually. So let's answer the first one. You have excess chromic acid in acetone. It froze on me. Oh, it's back. Excess chromic acid in acetone. What's the product going to look like? All right, so first question is, what does chromic acid react with? Alcohols, and it reacts with aldehydes, both, right? So I'm going to draw the skeleton. And I'll draw this one in a second. What do I get here? OH?
Oh,
A ketone. It's secondary, so you only get a ketone. What do I get up here? From here to here? I get a carboxylic acid. Even though it's not an alcohol, right? Chromic acid will oxidize aldehydes to carboxylic acids and primary alcohols to carboxylic acids. Now, here, right? They threw the stereochemistry in here just to confuse you. You know, in the mechanism, right, it doesn't involve this carbon. It involves the carbon directly, the alpha carbon, the one directly attached to the alcohol functional group. So this stereochemistry remains the same. So this should be like this. And then, if you're lazy, you just do that. But, right, this is the same as what's up there. Just a different way of writing it, so you need to get used to that. Now, let's say you do the same reaction with PCC. I'll draw the skeleton out. Let me draw it a little lower. Okay. What do I get here? Ketone. It still converts secondary alcohols to ketones. What do I get here? Yeah, so it doesn't do anything. This is already an aldehyde. It does not convert it into anything else. And then what happens here? It gets converted to an aldehyde. And again, oops, I screwed something up. I just see it now. This should be CHO here. I left a carbon off on the top one. Oh, no, wait. Actually, I had it right the first time. My bad. It's the one down here I got wrong. I thought I had it right the first time, and I outthought myself. This should just be CHO down here. Again, that's just another way of writing an aldehyde. Oh, interesting. Sorry. And then you can do all kinds of things with that molecule that I'm not going to talk about. All right, so for the PCC, it's usually something aprotic, so like methylene chloride. I don't know what else. What's that? Yeah, I guess you probably should. Just don't put like methanol in there or water. If you do, by the way, if you do PCC with water, it'll do exactly the same thing as chromic acid would do. Okay, it'll oxidize primary alcohols all the way because the water is. If you add water as a solvent, it'll provide the source for making the diol from the aldehyde. So PCC, right? If this is an aqueous solvent that's down here, the water would protonate, well not protonate, but form the diol here, and then this would get oxidized to this, and then this would get, because it's a primary alcohol, would get converted over to this with water present. Okay. All right. A lot of the rest of this stuff, I'm just going to show you that it's there and that it's useful. Okay, so you know this should look familiar to you. This is the functional group interconversion charts that the book has. They also make another one for chromic acid oxidations, right? So I would probably make one more. But chromic acid can convert a secondary alcohol to a ketone, and you can convert it back using lithium aluminum hydride. PCC can convert a primary alcohol to an aldehyde, and lithium aluminum hydride can convert it back into an alcohol. You can also write down here sodium borohydride. That's another option. And then one thing that you should make a chart out of, probably add to the chart, is that you can take primary alcohol, convert it to a carboxylic acid, and then the only way to convert it back is lithium aluminum hydride. So LAH will convert carboxylic acids all the way back to primary alcohols. So that's in essence a route that's not shown on here. For a primary alcohol, you would start from here, and then on the other side of this, you could put a chromic carboxylic acid, and then show the conversion from aldehyde to carboxylic acid, and then all the way back. Okay. Maybe like this. Let me draw it out on the board. So you would have, in addition to what's up there, all right, this is PCC, and then coming back like this, this is either LAH and water, or NABH4 in like an alcohol. So either one of those would do that. And then over here, you could also have carboxylic acid, which you can go like this, and this is going to be chromic acid, H2CrO4. And you can go back. Let's see, can you go direct? Oh, we don't know a way back, do we? Yeah, we don't know a way back. There is a way back. SOCl2, and then it's a hydrogen catalyst, but it's one of the deactivated hydrogen catalysts, and I'm trying to remember what it's called. It's got a name. I'll look it up, but there is a way directly back. But actually what you're doing is forming an acyl halide, and then you're using hydrogen to displace the chlorine. Okay? And then you can go like this, and that's just chromic acid. And you can go all the way back like this. And this is LAH. So I'll look this one up. I think it's called Roseman's reagent or something like that. I have to look it up. There's so many reagents that are named. It can get confusing. But it's a hydrogenation reaction with like poison catalyst, I believe. Okay. Questions? This one looks relatively like tame in comparison, right? They're showing these in terms of oxidations and reductions. I think it would be good to know if it's being oxidized or reduced, because if it's being oxidized, it's probably one of the oxidizing agents you've been taught, like chromic acid. And if reduced, it's probably hydrogen and catalyst or LAH or sodium borohydride. Okay, this is the crazy one. So this is what they eventually do to you. They put it all on one page, right? This shows like aldehydes and ketones and how you go back and forth, and if you have a alcohol and an alkene, how you go back and forth. So this is a great, like when you're doing synthesis problems and you think to yourself, don't think about the reagents, just think about what transformations you can do, right? Get the transformations and then see if they're on this chart. Use the chart to help you with your synthesis until you learn everything really well. I like that chart, but I'm not going to say much about it. Because there's, right? It's all the reactions from last semester and this semester. Like it includes like over here, right? This is the branch for radical reactions. And then the formation of alkyl halides, and alkyl halides can be converted to alcohols or alkenes. Alkenes can go to alkynes. There's stuff that's not shown, like alkynes can go all the way to alkanes, right? They don't show that, but there's things on there that aren't on there, but most of the common things are up on there. Okay. I'm going to skip this slide, but you do need to know how to do these things. Most of this is, reviewing like what you can do with reagents. So I'm going to skip over these, but make sure you look over this section because it puts all the reactions and uses them for making things, okay? All right. Yeah.
Will something like that be on the end of every single chapter?
Pretty much.
Oh.
Pretty much. Yeah. Little bits and pieces, maybe not the big page thing, but I think the big page one is in this chapter.
But at every end of chapter, it'll make us synthesize using stuff we know.
Yeah.
And the new stuff we just learned. Okay, cool.
Yeah. Those are like the challenge problems. Or the cumulative problems. Yeah. All right, I'm going to stop this recording and I'm going to start another one for the next slide series.